We're going to go over in-service inspection approaches for lead-cooled fast reactors. It's really how do you see inside of a lead-cooled fast reactor. But in order to figure out what that problem is, first we need to develop what's actually required by regulations. So we'll go through the general methodology and then work through it. So the agenda, we'll go through the introduction, base research questions, and then develop the problem with the methods and scope and the lead-cooled fast reactor parameters. What we know now, what's garnered by regulatory guidance, and then what current technologies are available. And then we're going to apply some basic physics to those current technologies in order to check the feasibility of if you can take something that's on a water-cooled reactor or a sodium-cooled reactor and translate that to a lead-cooled fast reactor. We'll summarize, look at some future research in case any of you want to work with Dr. Smith, and then go through questions. So why a lead-cooled fast reactor? Well, currently there's a big gap for scalable technology as far as nuclear reactors go. Most of them, if you want to build it and make it economically feasible, you have to make a giant reactor. So it's very hard to scale that down to a smaller size. Lead gives you that opportunity. It's one of the 6 reactors that's currently being inspected for advanced reactor design technology worldwide. There's 50 different concepts in that advanced reactor design, and about a dozen of them are lead right now. And overall, it's just a technology that's being developed, but we're trying to fill some of the gaps in that development. So for our research goals, first we have to identify what the requirements are for inspection, determine the critical components that we need to inspect based off that criteria, and then propose inspection methods using general physics in order to inspect our reactor. So research questions follow along that same line. What are the in-service inspection requirements? Is there current technology that's available? And then what kind of physics? We're exploring ultrasound, electrical testing, and thermal testing and that's all being developed and currently used on sodium-cooled reactors, so we're applying that technology to a lead-cooled reactor. And then currently, lead-cooled reactors use out-of-service inspections. I'll go through that a little bit at the end. So this is a general lead-cooled fast reactor. Most of them, because they're opaque, use a pool-type reactor, so it's a big swimming pool, and all the components are removable. Once again, these are in the design phase, but you have a large reactor vessel with an air gap between that and the containment vessel. You have your core assembly, which is anchored at the top, and that's actually above the free lead level. You have the lead level shown here by the dotted line, having all the radiation components inside of it. And then lead gives you a natural gamma radiation protection. That's one of the reasons you can scale it really well. And then there are a lot of different designs, but most have some kind of a dip cooler or steam generator. And they can either work by natural convection or actually pumping lead into the steam generator to circulate it throughout the reactor and act as your primary coolant. So design challenges with this. Well, one of the biggest is most are in the design phase. So there's currently one under construction by the Russians, the Brest reactor, but there's not a lot of published material on it. And with that, there's also not a lot of for the inspections that are required, there's not identified technology to accomplish those inspections. There are a couple other problems. The weight of lead makes it a big seismic problem, and the opacity of lead, high operating temperature, and the corrosiveness of molten lead make in-service inspections a challenge. Overall, today we're going to look at the identified technology, see if we can work that out, and then go through the opacity of lead. And those are really the 2 biggest problems that we've identified that are unique to a lead-cooled fast reactor. So methodology, first we're going to look at the Nuclear Regulatory Commission design criteria and apply that to a lead-cooled fast reactor. Currently, design criteria it's not specified for a lead-cooled fast reactor. It's actually a general reactor design criteria that's published, and it's specified for water-cooled reactors, both light water-cooled and heavy water-cooled. They did make a draft design criteria, but that draft design criteria is for general reactor design. It came out about 3 months ago, and it's not published as regulatory guidance at this point. So after looking at those criteria, we'll identify the lead-cooled fast reactor parameters for testing, compare that to current technologies available, consider basic physics theory to determine the feasibility of conducting those inspections using current technology, and then see if we can work it out under lead-cooled fast reactor conditions. So design criteria, like we just discussed, there's 64 drafted design criteria, and of those, we dug through as about a 200-page document, and we identified 8 that are specific to in-service inspections of lead-cooled fast reactors. Those are shown here and on the next slide. So of those 8 inspection criteria, you can break it down into, we've got inspection testing of electrical power systems, protection systems, or emergency core cooling systems, but really as applied to the lead-cooled fast reactor, you can break it down in 4 categories of general system functions, component integrity, the coolant characteristics, and then atmospheric cleanup and radioactive release control. With those 4 categories, we then refined it to what is unique to a lead-cooled fast reactor and doesn't have identified technology. So general electric, reactor functions, atmospheric conditions, those are very well-developed technologies across the reactor spectrum of currently functioning reactors, so they're outside the scope of this research. And then with the coolant, really chemistry is a material science problem, and that has identified technology with both molten lead filtration and chemistry of figuring out what the composition of lead is. And then the lead flow rate we found out could be done through temperature distribution across the reactor. So the 4 things we're going to look at today are the temperature, and then within the components, we're going to look at the steam generators, which are those dip coolers, the core assembly, how you see a good picture of what's going on inside, and the reactor vessel to make sure there's no cracks or leaks or defects within it. So one of the problems that we identified earlier was there aren't a lot of design parameters that are published. So we took 2 design reactors. That's the European lead-cooled system. It's a demonstration reactor that has follow-on reactors, or follow-on designs, but it has a lot of the published parameters as far as the dimensions and the temperature distribution across the reactor. So we'll be using this for our basic physics design testing. Yep.
Sorry to interrupt. What's FLL?
Free lead level.
Okay. Thank you.
So going through this, it's the core diameter, the height of the core, that's the reactor vessel diameter, the base to the free lead level. So it's the reactor vessel base to the free lead level. So this would really be your inspection area. And then the thicknesses of the steam generator, thickness of the reactor vessel, those are for our electrical testing, which we'll go into. And then the second reactor we're going to be looking at, so we're kind of combining these 2 into one, was the Westinghouse demonstration lead-cooled fast reactor. And this reactor had most of the material properties published, and a lot of these were tested. So they use D9 stainless steel, which is basically it's AC316 stainless steel for most of the components and the outside of the reactor. And that stainless steel, to prevent corrosion, has a aluminum oxide coating on it, which just prevents against lead corrosion at higher temperatures. And then it has a uranium oxide fuel, and lead is just, we're testing pure lead in this instance instead of lead bismuth eutectic is the other reactor design. So looking at current technology available, we'll delve deep into each one of these, but 4 reactors that are currently functioning and have in-service inspection equipment, the 3 that we're going to be looking at that we think can help with lead are eddy current testing. This leverages Faraday's law of induction. It's just producing an electromotive force to produce a magnetic force, and then using that next to a material to figure out if there are any defects. I'll dive a little deeper into that. Thermocouples, which we hopefully learned about in semiconductor spots with Karmsori or but it's a difference of two materials and they each have a characteristic impedance. And when you apply temperature to it, it gives you a voltage difference, and that will can be calibrated to give you a temperature reading. And then ultrasonic arrays, which there are two different kinds of transducers that you can use in ultrasound. And you can put them in two-dimensional arrays, three-dimensional arrays, linear arrays, but really what we're focusing on is the feasibility study, so making sure that this is possible. So we'll be doing the one-dimensional acoustics problem just to make sure that this is a possible technology. So starting out with thermal, we started spending many days looking at the diffusion and the advection equations and trying to solve that for 3 dimensions. And after chasing rabbit holes for about a week, noticed that the advection rate, the lead flow rate, was already published in Westinghouse's parameters at 1.4 meters per second. So instead of trying to solve the temperature distribution across a reactor, why not just compare that to the diffusion rate of how fast does heat diffuse away from your reactor core, and then see if that's comparable to the convection rate. And so we looked at the thermal diffusivity of the reactor, which is dependent on the conductivity, density, and the specific heat at constant pressure. And then solve that for the upper and lower temperatures within the lead-cooled fast reactor to get a very minuscule amount of diffusion in comparison to the convection rate. So that tells us that with the thermocouples that are possible by material science, by putting those in the direction of the lead flow path, you can both get a temperature distribution and the lead flow pattern across the reactor. And it makes it much more simple. So eddy current testing, this is kind of a picture of how eddy current testing works. You put an alternating current in a coil of wire. It induces a primary magnetic field, and then when you get that close to a material, that magnetic field induces eddy currents. So it's a secondary electric field induced by your magnetic field, and those eddy currents produce a secondary magnetic field, and then when you calibrate it, it has a characteristic impedance of the entire system. So when you come close to a defect or a crack or something like that, it will change the impedance and let you know that something's going on and requires further inspection of the reactor. There are a few different ways to look at penetration depth, but the one I found the most was the penetration depth based on conductivity, permeability, and angular frequency. And by taking that and graphing the frequency, because everything else is material properties, against your maximum penetration depth, you find that it's very well suited for inspecting steam generators, which have a 5 millimeter thickness. That's great for steam generation, but eddy current testing is also used on the reactor vessel. However, a lot of the reactor vessels are either thinner or they inspect it from the inside of the reactor. And for us, inspecting on the outside of the reactor vessel comes just outside the parameters for normal eddy current testing. So then we start looking at ultrasound. So for ultrasound, the 3 main things we're going to look at are the absorption, so how much sound gets attenuated in whatever medium you have, the reflection transmission, and then just checking the far field conditions to make sure that we can simplify the problem. So first, the attenuation of sound in lead and steel is a very large equation. So in order to find all these constants, we actually found a tape or a book that had a database of thermal physical properties of different materials that were going to be used in advanced reactor design. And all those had a lot of tabulated data, some best fit curve lines, and you plug in your temperature and your material properties, and it spits out a constant for you. So we determined all of those for the upper and lower limits of lead within our reactor. And then for comparison, we determined for sodium because this technology is currently being used in sodium-cooled fast reactors, and found out that lead actually attenuates almost an order of magnitude less than sodium per distance, which is great. So applying that to a range of different frequencies within the ultrasound spectrum, we found that in order to go from the reactor vessel to the core and back. This is just one of the parameters we looked at. So if you wanted to use 1 megahertz as your ultrasound frequency, then it would be about 65% relative intensity is what you would get over that travel distance. So just gives you a good range of frequencies that you can use in conducting ultrasonic inspections across your reactor. So the next thing we looked at was in steel. Now steel, luckily, if you're talking about the reactor vessel, already has some published parameters for absorption. So we can use that to do the exact same thing, and found out that for our reactor vessel thickness going full travel distance through it, it works very well across our entire range of frequencies in ultrasound. So the next things we had to do were check far field conditions to make sure that our transducers would work, and check the reflection and transmission intensity. So for the far field condition, go back one. Conditions we used, it's the distance that you're traveling is much greater than A, which is the radius of the transducer, and then the radius squared over the wavelength of the 2 far field conditions. And what that does is it allows you to assume that the wave is a plane wave instead of a spherical wave or a circular wave or whatever else you want, and that makes your calculations much easier. And the much greater than, some people use a factor of 4. Just to be safe, I used an order of magnitude, so 10 times greater than. And in doing that, transducer radius for sodium-cooled fast reactors was 0.64 centimeters, and we used the general frequency range of 1.5 megahertz, and found out that it's a very feasible design, so it definitely meets the far field conditions. Last thing we looked at was the reflection transmission intensity coefficients, and this is where we ran into some interesting results. So lead is extremely dense, so therefore it has a very high acoustic impedance, which is the density times speed of sound. And because of that, molten lead is very comparable to all of our components inside the reactor vessel. So you actually get a very small reflection, about 6%, when it bounces off the components and comes back. At first we thought, okay, well, sodium is probably comparable, but sodium is about an order of magnitude less. So you get about 80% reflection. It's like, oh wow, I might run into a problem here. But when you combine this with the absorption coefficient, because sodium attenuates almost an order of magnitude more than lead, or the sound in sodium attenuates more than lead, the relative intensity drops off much faster. So over our typical reactor size, you would actually get more of a signal in lead after about 6.5 meters, which sodium reactors are also about 3 times larger than lead-cooled reactors. So signal over the distance of your reactor, you get more reflection back after the travel distance is taken into account. And then looking at the reactor vessel boundary for your reflection transmission, you get about the same 5.4%, but it's a very short travel distance, so you get almost no attenuation. And when you're looking at the reactor vessel, you're looking less for what the picture is, and you're looking more for defects. So if you have a defect, it's going to greatly increase the acoustic impedance at that point, and you'll get a very clean signal back. So it's actually good that we don't get a lot of reflection at the boundary, because you're looking for things that are wrong on the reactor vessel, not a clean signal going through. So summarizing our results, the coolant temperature and filtration, these can be done through temperature with our N-type thermocouples over a continuous period. Filtration, that was identified as something that's not really unique, but it has to be done during periodic outages in the steam generators. Core components, ultrasound, the core temperature with our thermocouples again, the reactor vessel integrity, eddy current testing wasn't quite successful, so ultrasound and then the steam generator integrity eddy current testing would be more than sufficient for. Overall, there still needs to be more testing done to ensure that you get a distinguishable signal in ultrasound, but eddy current testing is fine and temperature testing is fine. And it is more favorable than sodium, which is currently being used and deployed in the world. So future research looking at computer simulations with 3D multiphysics solvers, which are each one of those individual testing tunnels could be a research project on its own. Physical research, which you can't really do it with molten lead around here, but molten mercury has about the same acoustic impedance as molten lead. It's very, very comparable, so that's a possibility for conducting ultrasound testing. And then policy and economic research, which is the big hurdle we're trying to get over. And references. Any questions?